Good afternoon. You almost got me there. I know a lot of you were curious about this. I did not successfully finish both of my sandwiches. I had like 2 bites left. I was going as hard as I could in there. I know you all follow along every single unhinged ramble I say in Discord, so you're probably really curious about the sandwiches. Today, I am on all of our favorite operating systems, Windows. You don't believe me? Look at this. I'm going to press the Windows key on my keyboard and look.
Gross.
You should
Windows.
try to open Python in the terminal.
You think I should try open Python on the terminal? So, fun fact, this is like Windows like 7 or something. So I don't even have Windows Terminal on here. I have whatever this thing is.
Oh, it works this time. So you're not using Windows Terminal.
This is the one that doesn't work.
This is the new Windows Terminal.
This is the one that doesn't
Yeah,
work.
there we go.
Yeah.
There you go. Classic.
Not to worry. I am also running the good operating system. Over here we have, you can tell, wait, how does that not zoom in? Okay. You can tell this is definitely Linux and not being hosted on Windows, because if you type Python 3, you get Python. And if you type Python, you don't. Now, wait, you can't? I thought I could still, oh. Sudo apt install. Can I still get Python 2? No.
You have to install Python 2 specifically.
But then will it alias to Python?
We'll find out.
We're about to find out, folks. A lot of people think that there's... Please. No! Okay. Okay.
Maybe Python is Python 2 is what you want.
Maybe it's time to put while we're at. Anyways, so I successfully got Rust running on this. There's cargo, and I can cargo run something. So I think I can do demos today. All right. So today we're learning about Unsafe. Maybe Jimmy already taught you Unsafe. That's fine. Jimmy can basically do anything due to the protections on free speech afforded to us all by the First Amendment. Oh, did you have a question about that? Okay, yeah, since there was a question, the amendments are one-indexed. They were written by data scientists. So if you think, okay, I'm going to say something. If you're a data scientist, you have to promise to not get mad. Dang it. Oh, no, you got here on time.
Perfect timing.
So if you find any logic errors in the amendments, I would like to point out they're one-indexed. Okay? All right, that's all I'm going to say. We're going to keep going from there, okay? Today we're going to learn about Unsafe. We're going to learn about UB. What's UB stand for? Don't answer.
Oh, I thought you said UV. Ultra bad.
Ultra bad.
I like that.
That's pretty good. Yeah.
That's actually pretty close.
I guess we could learn about UV. It's not really relevant to this course.
I know, that's why I was UV.
And then
I thought you were
dereferencing.
doing, like, more weird Python shit.
I should start using UV.
Python's, you know, the more I talk about how much I hate Python, the more I negatively polarize myself into liking it. So here's an exact quote from someone who presumably is trying to be edgy. The dark arts of unsafe Rust. The knowledge is provided as is without warranty of any kind, express or implied, including but not limited to the warranties of unleashing, come on, like really indescribable horrors that shatter your psyche and set your mind adrift in an unknowably infinite chaos.
Someone got a thesaurus for Christmas.
I'd like to point out that it allows you to interface with C++, so that's pretty accurate.
But like, is this not a little bit
Yeah.
excessive?
It's a little bit
It's a programming language, okay, right? Like, it's not like the computer's going to like start munching or something, right? Like, it's, you know, you're gonna do a null pointer dereference and hit a segfault. Like, that's the scariest thing that can happen. Okay, that was not true. That was a massive understatement of the scariest thing that can happen. As long as you're not connected to the internet, the damage will be confined to your machine no matter what you do. I think that's true. Okay, so there's things that we care about and things that we don't care about. One of the things I care about a lot is how big integers are. I'm actually giving a talk at a quality engineering conference tomorrow about caring about how big integers are. I pointed at Portland because that's where it is. So it's not a very good conference because it's in a declining regional city. But nevertheless, it is walking distance from my apartment. So there's pros and cons there. So every once in a while you care about how big an integer is. Okay, I'm going to say one thing, and you're allowed to get mad. Why is the Rust default integer 32 bits?
What should it be?
That's about big enough.
64?
It should be U size.
See, that's what I'm saying.
It should be U size. That's what I think.
It should be U size, and they should only support 64-bit architectures.
I think the
Yeah,
default
still.
should be
Don't know about that one.
something weird so that people want to change it.
Oh, to like
That's what they did.
to persuade you not to do
But
it.
like I don't know if that's
Who uses a 32-bit signed integer?
When was the last time you used a 32-bit signed integer?
fair enough.
Right?
But I feel like an i8 or something would be
I would appreciate an i8 or U8 so much more.
Yeah, if you're gonna not default to 64, you should default to like 8.
Yeah.
So that like.
Either the
memory
smallest or
gains
the
that.
biggest.
default at 16.
Yeah, for sure. Smallest or
And also,
Either
like-
make it pointer sized or bite sized.
Well, you don't know what the pointer size.
Yeah, that's why I say U size.
And you can
That
have it
we can
dynamically
change.
update. Like if you plug something in that's too big, it dynamically updates to be something bigger. So it's big brain.
Oh, like Python.
Yeah, like Python.
So we're gonna have a variable size. We're gonna have an ix. Wait, no, hold on, just one
I
sec.
think this is to not confuse people who learned C first, but didn't learn it super in depth.
Where
think
is?
that's the whole
How do I
reason.
find my
It's just
classes?
the value in
32 bits is
CPU.
about big enough for most applications.
What is going on with the internet?
Yeah. Without being excessive.
What is? Okay. Anyways, I was gonna show the ix assignment from last term, but I can't get the internet to load. Anyways, okay. So, funny story. Many years ago, C++ came into the world, and people have a lot of opinions about that, and most of their opinions are correct. A lot of the C++ programmers were curious why they weren't allowed to add C++ to the Linux kernel. And the apocryphal tale I didn't go back and dig through all the mailing lists, okay, I have a job, was that the Linux kernel developers said there was nothing wrong with C++, there was something wrong with C++ programmers, right? Let me just say, the Unsafe Rust programmers, when they start their book like this, does not inspire confidence. Fun fact, I was at the Portland Linux user group this Sunday. I volunteer there. You're welcome to come up anytime. It's a long way from you. They've asked for you to come up there and give talks if you're curious. They keep saying, Calvin, why aren't your students giving talks? And I was like, they live in Salem. Anyways, what they keep pointing out to me every time they see me writing Rust while I'm at the Linux clinic is that C is also memory safe if you write it correctly, which is true. So you can always simply write good code. Now that said, this is a Rust class. Why is it a Rust class? I've been persuaded that by teaching you in Rust, you'll learn to code better. So fair enough. We're actually going to teach you to be able to write memory safe C code by teaching you to write Rust, which might work. Okay, so blah, 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 unsafe. How many bits is in an integer in Python? You all know this. Nobody knows. Wait a minute. That says Python, not Python 3. So actually you have to, it's a decision tree. You check your Python version. And it's Python version 2. It's in, actually, what is it? It's an i32, right? The implementation type is an i32. And if it's Python 3, it's actually a very cool implementation. So there are 30-bit integers with a sign bit and a nails bit that expresses whether the integer extends further up. And you can find this nails bit if you look at the GNU Mixed Precision Integer library, which I'm assuming Python uses under the hood, but I don't actually know. Okay, here's a fun question. How many bits is this array in Rust? So that's an i32 array. Very, very hard for me to not accidentally call that a vector. So I just taught an AI class where we were actually using the mathematical formulation of vector as in like a multidimensional scalar. So this is a mathematical vector, but it's not a language theory vector. So that's an i32. There are 3 of them. They're all 0. How big is that thing? The only thing I know for sure is it's not 32 times 3 because there's additional data there of some kind, right? So there's some sort of implementation details there. I don't know. I'd have to check. Who could possibly care how much space the empty, tuple, right? Tuple? Do you all really say tuple?
Yeah.
Yes.
Who taught you to say tuple?
Me.
I think Google, yeah.
Tuple.
There's no O in that.
There's a U with an E after it.
That would be tuple.
Okay.
Okay, we like that? Okay, all right. That's right. Okay. If you're going to commit to that bit, then that's fine. Okay, so sometimes it matters. Why does it matter? I really disagree with this claim that the most common reason is performance. I don't think that's true at all. I think overwhelmingly the reason this stuff matters is you're in embedded systems, you're doing automotive, you're doing aeronautical. Professor Rachel Brown's partner works at Daimler of America in Portland, writing real-time operating systems for battery packs. None of those are 64-bit systems. They're all different size of bits. Many of them are probably don't have division on them or something, right? You have to use some language to write code that determines the battery operations of your semi-truck, right? I don't know by line of code how much of the world's code is embedded, but I'm guessing it's a lot. And the reason I'm guessing it's a lot is there's a lot of embedded systems, and all of the non-embedded systems, all of the laptops, they're basically using all of the same code. So even though there's a high volume of code that's written to run on data centers and so on, I think just the sheer amount of embedded stuff, the number of smart toasters and smart watches, and I guess the smart watches probably all run Android. Maybe that's true. But they have accelerometers in them and stuff. So I think, to me, it's the overwhelming majority of the time where you care about how many bits something is you're working on something other than your laptop. And you can be working on something other than your laptop for a variety of reasons, Internet of Things, you're doing agriculture, you're doing whatever. Separately, if you're working for one of the cloud giants, my impression is if you're running workloads millions of times a second, the performance does matter a lot, and then you start thinking very closely about how many bits you move around. I am wondering if the Rust i32 design decision was made thinking that perhaps someday lots of Rust code would be running on devices where somehow 32-bit workloads are accelerated. My understanding is that machine learning workloads are moving to lower and lower bit precision. And so, for example, there was a recently introduced, I think, 8-bit floating point standard, so you can do machine learning on 8-bit values. So people that are doing exascale data, well, maybe you can do 8 times as much machine learning if you use 8 times smaller integers to store your information. Okay, that is a performance benefit. And it's not necessarily just a performance benefit related to speed, it's also related to heat and energy. Okay, so this matters when you're working with hardware. It matters when you're working with operating systems. Why? Because working with hardware and working with operating systems is the same thing. What does the operating system operate? It operates the hardware. It takes a piece of hardware and provides an interface to some higher level organization, such as a programming language or a human or something else. And once that operating system sort of obscures some of the complexities of working with the underlying hardware, it is easier to get your code to run. It would be, I claim, very difficult to run a browser on a CPU. I don't think anyone has ever written a browser that runs on a CPU. All of the browsers assume an underlying OS, and the browsers are one of the most sophisticated pieces of machinery. Certainly there's not any image editing programs that run directly on bare metal. That would be crazy. Something I have been thinking about quite a lot when looking at sort of the operating system stuff is the operating system provides a series of abstractions up to basically heap allocated storage. Now it is often the case that modern programming languages provide one additional level of abstraction above that. For example, the Rust vector type, the Python list type. C++ has vectors. Did I make that up?
Yeah, it does.
And then C doesn't provide that because it's a good language. Okay. So, when implement details start to matter in a safe programming language, you have a problem. And the problem is you have to make a decision. So perhaps it's a problem in the sense of a problem statement, not a problem in terms of an issue. So when does this matter? The classic example I always give is actually sort of motivated by the integer example. I suddenly need to deal with a number bigger than naively fits inside my integer type. Or in the case of Python, I start seeing irregular or inconsistent behavior because I have different types of integers floating around that have different memory behavior. So when this happens, when my code starts to behave in an unpredictable manner due to some underlying feature of the hardware that cannot be managed consistently by the language, you have to do one of these 3 things. The first thing, and this is sort of my favorite to do because I think it's fun, is you just change the code a little bit. And you change the code a little bit to suggest or trick or perhaps prompt the compiler in order to develop a certain type of executable that matches your expectations of what the executable should look like. Often this is done by taking structures and combining things together in a certain way, but there's a variety of other ways to do this. One of the most common examples of this is using bitwise operations. So it is rarely the case that bitwise operations are actually efficient. It is often the case that human designers write bitwise operations perceiving them to be efficient in order to try and accomplish some logical goal. There's an interesting paper on this called Stoke that you should read sometime if you're looking for it. And that doesn't always work. Let's see. You can adopt a more unidiomatic. Shouldn't that just say less idiomatic? Or cumbersome design to get the desired implementation. So to me, this is actually the Rust approach. Rust forces you to specify large amounts of context about the code you write. There are pros and cons to this, but it causes Rust to be very consistent. It causes the LLVM to be able to reliably compile it into the machine code you would expect to get. So if you write a for loop in Rust, you're going to get some underlying control flow in your assembly code that looks an awful lot like a for loop. Can you get around this? Yes, you can embed assembly, you can use external calls, you can do something else. Usually that's not a good idea. And then the last option is the option I have always used, and I think it's probably the option I always used because Rust didn't exist, which is that you sort of just write whatever code you want in whatever language you want to, and if you ever encounter a problem, you drop down to C, you do bit-tight specification of exactly what you want to happen. You say for every bit where you want it to go using the features of the language, and then when you get all of the bits where you want to go, you go back up to your higher level language and do whatever it is that you want to do. I most commonly experience this when dealing with network protocols. Network protocols often expect you to have certain bits in certain places. There's often C library functions that support this, and if there's not, it is very easy to specify a specific bit. Something that I find hard to do, I think you all looked at WC recently. Actually, let's see if I have it here. Is that right? Okay. Read input from files specified by null terminated names in file F. I don't personally know a particularly graceful way to input null terminators to a text file. So for example, here if I'm trying to do WC of source main, and do I have anything else? I guess we can also do like Do I have two cargo files here? We have cargo. Is that a binary? That's fine. And then, so I can WC cargo got star. Okay, so I can get this behavior from cargo. If I want to create a file F that contains null terminated names, I just didn't know a great way to do this. So I think, do I have, okay, I have that, okay. So I can create a file F, and I can say cargo.toml cargo.lock. And think about it for a minute. How can I put a null terminator in this file? And so to me, the solution, the way to do this is to drop down to a lower level language. I can do this with C. Let's see. Let's see, create. No, I don't really want to do that. I can use printf, and I think I can printf cargo toml. Does toml stand for Tom's Obvious Markup Language or something like that?
Yeah.
It's used for network programming. It's used in the cloud, right? I've seen it before. I can't remember where. So, using printf, which is written in C, I'm pretty sure I can just specify, using the C language convention, this escape 0, null, they just call it null, right? Yeah, so these are, I believe, null terminated, or perhaps I would call them, I think, null delineated actually, file names. And I'm saving that in file F. And then, let's see, is that going to work? Okay, and then I think I can WC files 0. Do you think the 0 there means they're supposed to be null terminated files? What do we think this 0 means? I think it's just to specify null terminated. And then we can get the same functionality. Oh, I have different order. That's reasonable, I think. Because T comes after L in the alphabet. Is that right? So I put them in non-lexical graphical order, so that's why I get different output. I do not know how to do this in Python. Presumably there's a way, right? But at some point it becomes easier to just reach for the lower level language when you're dealing with some other lower level feature and it asks for a null byte. Like, I don't know how to put null bytes in a string in Python. Obviously I could figure it out. Why would I figure that out? This is like 15 characters or something, right? So to me, this is how things were always done historically. I think Unsafe Rust is challenging this assumption. I'm sure there isn't some, I don't know if I want to say graceful because I'd be dealing with strings in Rust. I'm sure there is some way in Rust to deal with this. I love it when Rust developers talk about C because I feel like they're talking about me and then I get to be the center of attention. Unfortunately, C is incredibly unsafe to use, sometimes for good reason, and this unsafety is magnified when trying to interoperate with another language, which I would never do because I just write C. Care must be taken to ensure C and the other language agree on what's happening and that they don't step on each other's toes. What does step on each other's toes mean? I think that means data race. I think that means C writes some information to a certain location in memory, tells Python that a certain information is written to that location, and then those two languages have to make sure that they agree if the data is being altered in some way. That's what I think stepping on each other's toes means. So if you implement some C subroutine in some language, you have to make sure that certain memory guarantees expected by Python or JavaScript or the higher level language are actually being maintained by C. I think it is uncommon this happens because it is difficult to keep track of memory in C and in other languages. So what does this have to do with Rust? The Rust devs came up with this pretty interesting idea, and this idea actually existed in other languages, but I think never actually made it all the way to the light of day, which is that, well, let's just cut the language in half. Let's have sort of a default setting where a lot of things that can get you in trouble aren't allowed, but let's not force people into C if they want to do some of the things that might only work on certain hardware, or if you make certain assumptions about the network activity of the device, or if you make certain assumptions about what else is running on the device. And they'll say, okay, we're going to have this partition that is external to the main working operations of the language. We're going to call that unsafe so people know it's sketchy and not to use it unless they have to. But it's going to come out of the same compiler. It's going to create the same executables. It is simply the case that once you start including unsafe blocks in your Rust code, it is no longer guaranteed by the compiler that you're never going to read memory that you're not supposed to read and be destroyed by the operating system. Now, if you are the operating system, this might not matter to you that much because the operating system isn't going to destroy you. But it also might matter to you more because now that's a bug you have to deal with yourself. So Rust can be thought of as a combination of two programming languages, safe Rust and unsafe Rust. I almost think of this, to me, closer to anything else. There's sort of like the Python data stack, which is actually a little bit distinct from the underlying language. And they kind of feel like two different languages where you're sort of oscillating back and forth between these partitions. So we'd use, for example, a NumPy array instead of a Python list, even though kind of those are just both a vector or an array. And so there are these other languages that are sort of like concatenations of existing languages. Rust does so at sort of the systems programming inflection point. If you had the uncommon misfortune of taking systems in Rust with me last term, You only learned safe Rust. I didn't introduce unsafe Rust in that class. I didn't see the benefit of introducing unsafe Rust in that class. That does not mean I did not think about it. There was one assignment that I cut because I would have had to introduce unsafe, and I decided not to do it. We can debate the merits of that. And it is also the case that you may have gone out and written unsafe Rust yourself because you found it was the most reasonable way to solve some of the problems in that class. I made sure I had end-to-end reference solutions in safe Rust for everything in that class, which means I didn't ask you to do anything that forced you to use unsafe. But especially when we started dealing with some of the memory management stuff towards the tail end of the semester, I would not be surprised if you went out and used unsafe or something. And in that case, I say, quote, good for you. This is an exceptionally strong claim. I'm going to soften this on later slides. But when you get down to what the safe in safe Rust refers to, it is not saying, I think this is a common misconception, it's not saying your code has no bugs in it. It is not saying it can't delete the production database. It's not saying it can't contain an infinite loop. It's saying it can't read a memory address that it doesn't know it has permission to read from. And that's a very, very restricted subset of what safe means. I believe it is also the case that this means that there are type safety guarantees, but also like the type system is internal to Rust. And so like, what does that mean? You know, that like, it doesn't offer a form of safety that could exist in some other languages. So I really think, I complained a little bit about how like dramatic this is. The only thing they're letting you do is read from memory without the compiler telling you that's allowed. That they're only letting you do one thing, right? And that's a very powerful thing to do, but it's not some like groundbreaking thing that's never been done before. Here's something I want to do all the time, and I was actually a little bit surprised how painful this was in Rust. Those of you that had systems in Rust last term, remember I was doing a lot of sort of functional programming techniques where I would call a function on an object, make some modifications to that object, and then return the object so that ownership passed back to the calling function, right? Sometimes you just want to have more than one reference. I say two here. You want to have more than one reference to an object that's mutable. When do you want to do this? I'm pretty sure you want to do this if you're doing any graph theory. Have any of you done any graph theory in Rust?
It's exceptionally painful.
It seems like it would be awful.
You definitely have to think about it a different way.
Yeah, because
to
you
get it
like
to work.
you essentially can't have the classical way I would do graph theory. You can't have two edges incident on a single node. My sense would be, hey, you're doing graph theory. Some of that stuff's formally proven, so you know properties about it. So just throw the whole thing in unsafe. You don't care about it, right? The mathematicians made sure it's fine. It's not my fault if the mathematicians screwed up, right? I just go down and I find the first one of their offices is open, which is always Professor Sato right now. So, but like whoever's down there, right, and you'd be like, why'd you ruin graph theory, right? Not my problem. And I know this because I was pretty far through implementing a suffix tree last term, because I thought that would be a fun assignment to give all of you. When I found out that I couldn't do it a way I was happy with without unsafe Rust. So I canned the assignment and gave you something else. I don't remember what I gave you instead. I was like, oh, that's kind of sad because this is a very odd complaint. My sense is that computer scientists should be taught a bit of graph theory. So historically, I've used graph theory as motivating examples to teach memory allocation and management in the C programming language. Worked very well in C. In Rust, you're just not allowed to do that, so I had to come up with other examples. There's nothing wrong with that. But it's this very interesting case of the language pushing you to do things a certain way that causes you to think about whether that language is the correct tool for the job you're doing. And certainly C is not the correct tool to use graph theory. It just happens that C and graph theory are both awesome. It is also the case that Rust and graph theory are awesome and they don't play nicely together. When you are doing something like graph theory or implementing your own memory management because you know how much memory you have to work with, When I was writing C for my job, we weren't allowed to use malloc because we couldn't assume that memory allocation went through, so we had to do everything in fixed size arrays and work within those. And we verified those with tools external to the language to ensure we won't overburdening our fixed size memory arrays. If you know that whatever you're writing that Rust says you can't do, which is like having two mutable references to a pointer, you know, hey, I have written a proof or something, I think it should be that burden of evidence upon you, then pop on the unsafe tags, do the thing the compiler doesn't allow you to do, and you have some other form of guarantee that the code is going to behave in the way you expect it to. But be advised, Rust C isn't a theorem prover. It won't be able to infer that what you are doing is safe. It doesn't have that type of understanding of memory. It simply bans a certain set of behaviors, the most obvious one being multiple references. This allows them from happening, and then it is easier for it to be confident that compiled code is memory safe. Okay, I'm supposed to give you a warning. I don't know, whatever. Unsafe Rust lets you do some really unsafe things. Does it really? Sure. It's not more unsafe than any other programming language. It's just less safe than the rest of Rust. You already know other programming languages. I think, did I have Discord open at some point in time? Wait, do I care about this? Okay, so this code right here, DI, I guess it's calling C, so maybe that's cheating. If you look this code up on the internet, which you're welcome to do, I think you'll get, what did I click on? So here's like a pretty interesting claim. I hadn't seen this before. This is from 2013, which is probably before people were talking about Rust. I guess it was edited 22. So this is just Python code. If you read the linked discussion, you'll find some folks think this is so unsafe that it should never be used. And I think there's a comment, certainly not considered safe enough to post on Stack Overflow. Like, there's something so wrong with this Python code, you shouldn't post it on the internet where other people can find it. I guess I just object to that. Like, if someone's going to use this code, they should just do whatever they want. So, like, that's obviously going to segfault. But, like, who cares? So, like, I do think if you're writing intentionally secure code, so if you're writing code that's going to run on shared hardware, cloud, if you're writing code that you're going to distribute to consumers, you shouldn't write something like this. But like, what problem are you trying to solve by doing this, right? So there is this notion of things that are unsafe in other languages. Rust can't do things that are more unsafe than the things that you can do in other languages. So how unsafe is it really? I think this is editorializing. I don't think I've heard anyone else say this. But my sense is that Safe Rust is the true Rust programming language. Safe Rust is Turing complete. There's nothing you can't do with it other than write an operating system. And there's all of these nice features in Rust that wouldn't be in there if it were an inherently unsafe language. So the entire type system and the entire borrow system would not exist if unsafe Rust were the base case, right? And there's so many things you don't have to learn about dealing with, and namely they're dangling pointer and use after free, which is the same kind of thing. It's like there's just all this stuff you don't have to worry about if you stay within the side safe Rust. My sense, and I haven't delved into that this much because I'm allergic to using code that other people wrote, except compilers, is that the standard library is going to give you almost everything you need in general to avoid using unsafe, except in the case where you're interfacing with hardware. Is that true? Did you nod, Jimmy? Does that sound right?
Yeah, basically.
Yeah, so Really, you reach for unsafe when you're dealing with hardware. Now, when you're writing an operating system, you're only dealing with hardware. Okay, reach for unsafe, right? That's fine, that makes sense. But probably if you're doing graph theory in Rust, the actual way you're supposed to do that is sort of, well, I guess we used graph theory using serialized, deserialized?
Serde?
Serde.
I don't know exactly how, but other people I think Serde. I've heard lots of things.
Seared. Anyways, so we kind of did graph theory using that. So you can always go to some crate that has sort of paid the implementation cost and use that to do whatever the thing is you're trying to do. That said, here's something that someone has to do at some point. Someone has to write an operating system. Now, you never do. The operating system has been written. The reason you're learning to write an operating system is so you understand what the operating system does. Fair play, if you get stuck at one part, you can probably still understand most of the operating system. And separately also, you're probably never going to write your own standard library, but I do want you to have some sense or appreciation of what the standard library is, so you know when you're using it, and you have some sense of the memory costs of calling a standard library function and so on, right? But someone had to write that stuff, and when they were writing that stuff, they had to use Unsafe. Fortunately for us, because we have paid a heavy cost mostly to our sanity learning the semantics of Rust, Unsafe Rust has the exact same semantics, so the just gobs and reams of text that you have to write whenever you do things. Do you all remember the turbofish?
I love the turbofish.
I refactored like the entire thing I was working on this weekend to avoid using a single turbofish, and it was completely worth it. It was non-trivial. Turbofish is evil. But I do love the bastion of the turbofish. Okay, everyone, we're visiting the bastion of the turbofish. See if we can find it.
What?
Here it is.
What's with Rust users and weird pseudo-religious texts?
I do think that they should stop. The Guardian stands resolute. The turbofish remains undefeated. So if you want to take some psychic damage, you can read about the Bastion of the Turbofish sometime. I got nerd sniped by it once, and now I know the entire backstory, and I'm not going to tell it to you. Okay. So I think there's one thing that's really cool about Unsafe Rust that I really like, which is that it lets you do things to your computer that you want to do. And I feel like as the programmer, if I want to access some bits and the compiler's not going to let me, the absolute most invasive thing the compiler should do is make me say, I know this is unsafe and I'm willing to deal with the consequences, and then I should get to do whatever I want. And that is what Rust does. And so Unsafe Rust gave me enough control back over my device that I was willing to accept it as a systems programming language, and I think this has been the general consensus as well. I do think, I do think it's cool that you have to label where you're doing stupid things.
Yeah.
This is especially true for me because I stopped writing comments a couple years ago. And so unsafe is, in a way, it's just a comment, right?
Yeah.
Right? Yeah. There's probably some way to configure Rust C so it just assumes everything's unsafe and just doesn't bother me.
I mean, you just have like an unsafe. I don't know.
Can't you default it to unsafe somehow?
Don't think so.
I'm like, that's a bad idea. I don't know why.
What is Rust
I think
always
you'd
going
have to-
unsafe?
Like you,
I think you'd have to fork Rust C for that.
I might do that.
you can't just.
I think if nothing else, when I suggest merging it back in, we'll probably have a legendary comment chain. Okay. Quote Rustnomicon. We gain the benefits of using an unsafe language like C without most of the problems that come with trying to integrate it with a completely different safe language. I don't even remotely believe you don't get most of the problems. I think you get the exact same problems. I think there is some benefit that you have to look at fewer lines of code to find where the problem is if it must be in an unsafe block. I have never in my life found that to be the hard thing about debugging a memory issue. It's always figuring out what I meant to do and what I did instead, which is usually about knowing the number of dereferences I'm dealing with or the actual architecture of the memory object. All of, in my view, the difficult things about working with memory in any unsafe language are completely present in Rust, which for you as students is a feature because you get to still learn all of the same content. It is not of great benefit to developers. So I question some of the claims about the supposed productivity benefits of Unsafe. Again, I have maintained, and you should formulate your own opinion on this, and that's the reason I keep bringing it up. You should come up with your own opinion on why you think Rust is emergent and popular. My claim is still, basically the result type and the option type is forcing people to write high-quality code that doesn't skip error checks. Everyone knew they should be doing that already. Everyone was lazy unless the compiler made them to do it. It turns out it takes 0 seconds to write error handling code, and it takes 10 years to debug your code. So we should have been doing that the whole time. But it does seem like I could write a flag for GCC that just forces me to null check all my system calls. Okay. I want to actually enumerate what the safety guarantees are. Safe prevents the following things, and a bunch of these are weird. In the sense that, like, why would you say this? So the obvious thing is dereferencing. So using Unsafe, I can create, and so Rust calls them raw pointers, which I think is coming from C++. I don't really like that. I would call them numeric pointers. And why would I call them numeric pointers? Because the difference between a Rust borrow reference and an unsafe, I don't know, raw Rust pointer is that one of them is a language object, intrinsic, I don't know, it's a certain type of thing. And that certain type of thing doesn't support certain operations like addition and subtraction. A Rust raw pointer, which I would call a numeric pointer, is a number, and that number corresponds to a social convention that the operating system has told you at some point in time the memory of the thing you were looking for is at that location. Now, it might also be the case you just put in whatever number you want, then there's no social convention governing what you're doing, and that is the exact example we showed here, where I just throw 0 into a dereference and then immediately get an error, which is totally unsurprising. So when you change from working with language object pointers that have guarantees made about them by the compiler to numeric pointers, there's no way to be highly confident that if you add 8 to some pointer, you're still going to read something that you're allowed to read from. And so this is dangling or unaligned pointers. An unaligned pointer is a pointer that points at a region of memory that is inside some memory block. So on a 64-bit device, I most likely have all of my stuff sorted into chunks of size 64, which makes it very odd. The Rust default type is I32. And so I can read from the 37th bit of that. No sane operating system will allow you to do this. One of the reasons you shouldn't be allowed to do this is it poses a security vulnerability, where if you slightly offset bits, you can perhaps get the name of an assembly command that does something you're not supposed to be able to do. That's the classic example. Dangling to me is that's just a pointer that is no longer supported. So there used to be something at this memory address. It is not necessarily still there. It is not guaranteed to still be there. You don't know if it's still there. I can demonstrate that one quickly. Okay, so this was the example we used previously. I create some array. I find the ID of the array, which I store in a pointer. We can look at the ID. Again, this is a numerical pointer, right? I don't think that necessarily corresponds to a memory address. I think that's something in the Python runtime, but like maybe those things are bijected. Okay, then if I reverse reference that, I can look at the array, but I can also destroy the array using del. What this means is that pointer now is referring to a location, a numerically defined location, and the language is not guaranteeing that there is anything present at that numerically defined location. It was the case when I tested this previously that you could still... oh, that's interesting. Okay, we got something interesting here. So, after I deleted array, there is, I guess, still some list there, but the list doesn't contain the same values. I don't know. That's kind of cool. I didn't know that was going to happen. I sort of like that. So somehow internally, the bits that say what type that is are still set to say, hey, it's a list. Oh, we got it. We segfaulted Python. I don't know that I've done that before. Wow.
Well, there you go.
Cool.
Totally impressed.
I feel like such a sense of pride right now. Do you know how hard it is to segfault Python?
I did not.
You should try this on your own devices because I didn't get this to work on the other one. Okay, hold on. We're gonna try one other thing because now I'm curious. We're gonna do the same inputs on top of Windows. No! No! Stop! Al Gore.
It's so funny every single
Or no,
time.
not Al Gore. Who's the other Al? Paul Allen. Okay.
Sure. That's one of them.
I feel like y'all are not as tolerant of me as you could be. Okay. I'm doing my best. Do you know how old this device is, Indy? Okay. What were we doing? Okay, so we create an array. What's wrong with PowerShell?
You have to import something to get DI.
I have to write DI myself. I have to import C types to use this. So this is actually a little bit cringe because the correct way to write this is you say DI equals lambda object ID of. This is the cool kids version. See, that's cool, right? That's how it's done. Okay, so we take pointer and we store the ID of array in there. Okay, there's pointer. Check some. There's the same number of digits, pretty close. Okay, so then we can DI the pointer. Okay, cool. Now we can destroy the array. Okay, and then we still have pointer, right? It's still referring to the same location. So we can DI pointer. We do get, that is a list. I was going to check the type, but I might get a segfault when I do that. And I think that's a bit string that contains, that looks like
it
something.
contains the three Python and then the space and then the command to delete.
Yeah.
Oh.
I do not know what that is. I mean, because that's.
Oh wait, those are.
Wait, it's
those
thi-
are the
it's this.
commands to color the Python chevrons purple.
Yes. So this is.
And that's to make it white.
Yeah, this is that. Right?
Yeah.
That's cool.
It's the string representation of the command. Because you see how the Python caret chevrons are purple. That's using a terminal escape sequence, and the terminal escape sequence for that is backslash
Can I?
one semicolon 3 5 m. That's how you turn it purple.
On Mac OS, after you
There we go.
Oh wait, that was weird. Like the list, the pointer the array persisted for a while after I deleted it.
Yes.
Yeah, now it's gone. Okay, now.
On Ubuntu, it stayed forever.
Yeah, stay for even after you garbage collected.
Yeah.
Right?
Yeah. Okay. Wait, these are different types, right? Oh no, they should be. No, they shouldn't be, should they? This is a list.
It's a list
And this is a
containing
tuple.
a single string.
Yeah.
Z shell bus error Python 3. Is that a segfault?
Bus error. That's usually a memory access block, which is not quite the same thing, but it's pretty close. The bus errors are interesting. If my brain is large enough, I will introduce the bus on Monday. Okay. Anyways, I hope we all had fun here today. How do I segfault this? Wait, no, okay. I'm going to see if this gives me the future. So I can add something to this. We'll add 64. And what is that? That's the same thing, right? Oh, we did it! I'm pretty sure I did it. Okay. So I think by referring to a memory address before it's used and then trying to interact with that memory address, I broke it. I'm not sure. So I don't know exactly what that is. But, okay, it doesn't say seg fault because it's Windows, and Windows is a coward and doesn't admit mistakes, right? But, okay. Why were we doing that? To explain this, okay?
It's in the 7.
Okay. Calling a function with the wrong call types. You're all Python programmers, so you know this. If you try and add, what are we not allowed to add together? Sets? That's like against the rules. Wait, no, is that? That's the wrong error. Yeah, okay, I'm not allowed to add stats together. So what is this? This is a runtime type error. Rust protects you against runtime type errors, so you will not see that in Rust. Causing a data race when multi-threading. Multi-threading is for like another class. Executing code compiled for hardware other than the hardware currently hosting the process or not supported hardware. If your underlying hardware doesn't have a floating point unit and you attempt to perform a floating point operation, Safe will prevent that from happening somehow. I don't happen to have any hardware that doesn't support floating point operations. And I didn't know this because no one told me. Producing invalid values like something other than 0 or 1 for a Boolean. I had no idea Rust Booleans had to be 0 or 1. That was complete news to me. Did you ever encounter this?
Yeah.
Just doing low-level stuff that comes up? Or?
I mean, just if you ever specifically using transmuting between types, which is just
Okay,
reinterpreting, it's you encounter all kinds of things you have to be careful with with types.
And Safe protects you.
Yeah.
Okay.
But it's really fun.
It builds character. Okay, so what does Safe allow? It allows a deadlock. Can I get a volunteer to explain deadlocks that isn't named Jimmy?
Indy?
Indy's not in this class, unfortunately.
Oh yeah.
Oh, that's true, yeah.
Yeah, so you would not get any participation
I figured
points.
that's what a mutex is.
I prefer a read-write law.
Okay, so my sense is none of you know what deadlocks are. That's okay. Okay, so I am a website. I have a counter for my number of visitors. Is that a bad example? Are you judging me? Okay. I have a counter for a number of visitors. 1 billion visitors land at the same clock tick. So each one of them takes the current visitor counter out of memory, adds 1 to it, and checks it back into memory. All of these 1 billion operations occur at the same time, so all of those billion visitors check back in, 1 more than the previous number of visitors. So the visitor count goes up by 1 instead of by 1 billion. So how do you prevent this? You say, oh, I need a mutex, which stands for mutual exclusion. So you have to use some hardware intrinsic to make sure whatever alterations to the underlying memory is happening, only one of them occurs at a time. Then what happens? Well, you write your code wrong, so the first visitor checks out the mutex, increments the counter by 1, never checks the mutex back in. The other billion minus 1 visitors, they never get to increment the visitor counter, and it appears to them that the website is down. So that's a deadlock. And that occurs when multi-threading. Whenever you hear threading, I just always think of an internet application because multi-threading on your own hardware is like kind of cool, and then using the internet is awesome. So I just always think of the internet. Leaks of memory and other resources. Those of you that took the C class know that I was a big believer in writing memory safe C and C that did not contain memory leaks. I taught you about Valgrind, where you could examine executing code and see if it contained any memory leaks. What is that? That's where you ask the operating system for some memory you can use. You use it, you finish using it, and then you never return it to the operating system. If you do this enough over time, you get degraded system performance. Not really a huge deal anymore, much bigger deal when devices were under-provisioned in the ancient past. There's exiting without calling destructors. I was never really convinced that the Rust destructors are like super cool or anything, so I just never taught you about any of that, and I don't care about it. Exposing randomized base addresses through pointer leaks. That's kind of this thing. This can pose a security vulnerability in the following way. You have probably a C standard library somewhere on your device. Learning something about the layout of memory on your device can give a hostile agent information about where to look for certain snippets of executable code. Those snippets of executable code can then be run by the assailant correctly guessing the memory address and loading it through some other attack into an executable register. So what this means is that you should regard the actual numerical address of memory on your device as information to be kept secure. This is a new innovation. Many of the older languages that have different notions of safety, this wasn't even perceived to be a security problem at the time. So it is of some benefit that Rust is actually calling this out. But it is also worth noting that Safe Rust still allows you to do that anyways. Integer overflow. Those of you that implemented SHA in Rust know that we had to intentionally do overflow. And I had that like really mentally stressful day where I did a complete unraveling where there's different integer behavior in debug and release versions of Rust. And for some reason, this is considered okay. I'm still not okay with that. And then the last thing that is allowed, and I do want to point this out, is you can still write bad code in Safe Rust.
I do it all the time.
I haven't done it yet, so you'll have to tell me what it's like. That's not true. I wrote polars, and that's bad even if it works. Okay. Oh, Jimmy, I'm giving a talk on the Rust code that we wrote together that you didn't help with tomorrow.
Oh, okay.
Okay. They ask me questions like, why did you do it this way? And I always have to say, I don't know Rust. I don't know if you enjoy that or not. Anyways, okay. Here, students, you're all students, right? You want to publish before you graduate. Here's the list of my publications. Look, it's Jimmy. Did Jimmy write a single word of this publication? No, I had to write it all myself. And it's about Rust. Why did I do this in Rust? I was going to do it in Go, right? Do you know how much easier this would have been to do in Go?
Wait, what does the abstract say about Jimmy?
Jimmy.
It's just about.
Jimmy's the president of the CSSA. This was true at the time.
Yeah.
I did not write this. I explained the new engineering degree to them, and they called it this. Because I'm not allowed to call it this for marketing reasons. So just so you know, I leaked out into the world that we have an engineering degree here using Jimmy. So if you would like to be part of any other low-grade fraud, let me know. Because I love...
Fraud.
You're recording this, right?
Did I say fraud? I meant something other than fraud.
Is this going to be posted?
Not anymore.
You heard it here first.
Instead of fraud, I meant recommendations for jobs. There we go. Okay. Ooh, that was close. Okay, so here's 5 things Unsafe allows. I think you'll only do this when you're interfacing with C.
Yeah.
You know what I think about traits. Don't write them. Write functions. Access or modify a mutable static variable. Absolutely do this all the time. Rust is so conservative. No, you should just make everything mutable and then just always access it, right?
What could be the problem?
Yeah, that sounds brilliant.
Yeah, right? I mean,
Just add
Python
logic
lets
to
you
the
do
game.
that.
Yeah, exactly.
Like, don't access at the same time, but that's pretty easy.
Please don't do
Exactly.
that.
So now when I'm writing Rust code, I just put the entire thing in an unsafe block.
Well, I mean, you can
Am I
still...
stupid, or is there something wrong with accessing a mutable static variable? That sounds normal.
Until
It's
you start
static.
doing multiple things at once.
So you do
What are you trying to access for multiple
Okay.
threads?
Because Python's written in C,
Can
the good language.
you not access it on a single thread? Like,
Yeah.
in Safe Rust?
No, because
So-
You can't change it. You can initialize it using constant at the beginning of the program. Then you can read
What
it.
makes it mutable then?
And you can access it. You can even use interior mutability to pretend like it's static, but it's really not. But in that case, you do have to still declare it. That's
Why
something that
is
could
it
change.
mutable if you can't change it?
Oh god.
So why did JavaScript try and get everyone to start using const instead of let
I
and
like
var?
how you can use const like twice in one thing. in
Const,
JavaScript,
and it's still not const.
It's still not const.
Yeah.
So why is this? So I have claimed,
Okay.
I've never been persuaded by this, that it's like a good thing that Python doesn't let you edit strings in place. And I guess the reason for this is a bunch of people that didn't know how to program were doing weird stuff. And then the flip side is, how blasted easy would Wordle be if you could just edit that string in place, right? And so, like, Python, give me an unsafe flag, because I will turn on unsafe for Wordle. Okay, call an unsafe function or method. Obviously, if you do something unsafe, you have to say you're unsafe while you're doing it. And dereference a raw pointer. Obviously unsafe. I successfully triggered seg faults in Python doing that. Okay, so here's what you should do. Write your Rust code normally, but before you type anything else, open an unsafe block and then write all of your code inside the unsafe block.
What about unsafe functions?
What about them?
You didn't mention them.
No, I just did. It's a bullet point on the screen.
It's not a bullet point. But when writing
It's a numbered bullet point.
Unsafe just practice.
Okay.
It's different.
Here's an example of unions. Oh, let's run this code. Let's run this code. I wanted to run this code. Which one of these has Rust on it?
that one? Yeah.
Ah, heck Windows. Okay, all right. Does anyone else hate Windows? Ah,
Yes,
I do.
yes.
Yeah, there we go.
Windows needs to rise up.
Wait, no. Let's just remove F. Okay. Do I have? Okay, we have it. Okay. So, what is this? So I have a union called myUnion. Have I taught you unions previously?
I don't think so.
What should I use instead?
What is a union?
Okay, so a union, in this case, is 32 bits. It's the larger number of bits of the two, or the n types contained within the union. And sometimes, for some reason, these mythical creatures known as C programmers used unions back in the olden days when bits still cost money to save bits instead of using a struct. Because if this thing were a struct, then it would just give you 64 bits, and you can only refer to them. So no matter what happens in this union, there's only 32 bits, and then you determine the type of the thing inside the union by using the, what should I call that, like the attribute name, the field name? Is that a field name?
Yeah.
Okay, and so how's this work? I declare, can I highlight this? Is there a way to highlight line? Well, let's see. Oh, whoa, I'm in insert mode? Oh, because I copy pasted. Okay. I think I'm doing great, actually. Okay. So what happens here? I declare an instance of my union, and I specify that I'm jamming a float inside the thing. Okay. This is all well and good. This is totally chill. But in order to look at both the same bits, the same 32 bits, to look at them as both a float and a, that's U for unsigned? Okay. And as an unsigned, I have to use unsafe because it is unsafe to violate the typing agreements of Rust, because you might do something you don't want to do or whatever. Okay, all right. So this is against the law, but when I say unsafe, I'm allowed to break the law. So I'm going to drive back to Portland today, but before I break the speed limit, I'm going to say unsafe.
Right.
And then they can't pull you over because you said you were being unsafe, right? But the compiler no longer guarantees that you survive car accidents, right? So it's like pros and cons,
It
right?
was doing that before.
Yeah, it was doing that before. The compiler is your airbags. Okay, so down here, we take u.u, which is the unsigned representation of the union, which, by the way, I previously threw a 0 in there, right? But that's float 0, which is not all zeros, which we found annoying when we implemented float, if you all remember. According to the internet, this is the bit pattern for 1.0 and IEEE 754. I guess I believe that, because I don't have any reason not to. And then we can come down here to, what?
Did you write that?
Yeah, but I wrote it like a couple days ago. I don't have, okay, so I garbage collect in my brain very quickly. Like, very quickly. Like, I don't remember how we started
Is
this
that to
class.
say you forget things?
No, it's to say I garbage collect. All of the things that are important I remember.
Right. What kind of garbage collection do you use for your brain?
The good kind. I actually run my brain on a JVM. Okay, blah, blah, blah. Okay, so we can refer to different things different ways. Okay. Okay, so we type cargo and we type a space, and then what do? You look around the room, okay, and you see Indy, and so then you're halfway to typing run, and you stop yourself in time, you do backspace, and then you just do cargo R. Okay. And what happened here? We're able to interact with the same 32 bits as if it is a float or as if it is an unsigned. Is this unsafe? Yes, this is unsafe because Rust is a type-safe language. Why does it allow this? Because the existing C code does this, and Rust wants to have interoperability with C. There could be other reasons. I don't think there's other reasons. I think this allows other functionalities, but I don't think they would have been implemented this way for any reason other than interoperability with C.
It's just
C
the
can
top.
interact with anything else, so.
The unions were unions even part of 1.0 or they added later?
Let's run some more Rust code. I love Rust.
Honestly, it's definitely for FFI and no other reason. If you're using a union that is not for FFI, you're using them wrong.
So are you allowed to write to it without it being unsafe? It's only reading it that's unsafe?
Yeah.
Okay,
Yes.
Yes.
got it.
Because reading it was like interpreting it as different types, and that types.
Is this all correct?
It's the same with pointers. You can create pointers, but you can't read from them.
Why am I reading that word?
Okay. So here we have our next example. Why is this a const? Oh, it's a pointer. Okay. So I create a pointer. I name it PTR, which stands for Public Test Realm, for anyone that plays World of Warcraft. And then I create a code block. I set x equal to a value. The Rust book did some dumb value here. I did 1, 2, 3, 4. 1, 2, 3, 4 is a good value. You're unlikely to see that in memory. It's not a power of 2. Clearly someone just wrote 1, 2, 3, 4 because you can go like that on your keyboard. Okay. Then what do? I take the location of x. And what type of location of x do I take? I take the numerical location. And I take that as a const i32. And then I say, okay, this is the value at the pointer. I close my code block. Now, in theory, I didn't get this to work on my other system, but on the ancient system from prehistoric times, maybe this will explode. I couldn't actually get this to say anything other than 1, 2, 3, 4, even though in theory, x goes out of scope here and should no longer be there. I'm guessing if you exercise memory hard enough in this line, that's line 11.
I think it's because Rust actually takes everything that's been declared and puts it at the front to make sure you have the constant size stack. 'Cause there's no variable size stacks in Rust.
Well, then why is this unsafe?
Because it could be in a different stack frame.
How do I get to a different stack? Okay, well, we'll run this, and then we'll break it. Okay, okay, so we type cargo, we type R, and then our hand is hovering over the U key, right? And we look.
You already have a space there, it looks like.
Oh, that was an accident. I didn't mean to have space. Okay. Oh, no, I don't. Okay, so anyway, I don't know how to break this. Probably because I don't know enough about Rust.
You should forget X.
You could maybe try to do another variable after the big block of code, see if that does.
Oh, I even did like, when I was at home, I did like loops. It's just like, I don't know. Oh, I guess maybe I have to use this? Because that's optimizing it out, right? I don't know.
Well, you're not changing the pointer.
No, but in theory, this could be written to the same location as that, right? Because they're both the first variable.
In theory, it could.
In theory,
and the
it could.
compiler is at some point could be made to do that.
Yeah.
What if you run in release mode?
That's a good idea.
Did you not do that at all when you were testing?
I actually usually don't. Is there a way to run in release mode?
Yeah, dash release.
Dash release?
Yes.
There's not a single. There we go.
Yeah. Wow.
There you go.
Who knew? Sorry. My garbage collector. Okay.
Interesting.
All right, so we learned something today. We needn't say what we learned because it's so obvious. Okay.
Isn't that your job?
Okay, so here's things that are my job, right? I was able to successfully alter the stack frame to get some weird value, right? Here's not my job. Justifying why Rust has irregular behavior in release versus debug mode. That is extremely not my job, right? And this is functional behavior because that's a value in a variable, right? Is it a value in a variable? It's a value that can be accessed using a variable, right? I feel like I am under absolutely no obligations to justify the release versus debug functionalities of Rust. That's a bridge too far for me. Thank you for asking. I appreciate the question. I did write a version of SHA 512 that only worked in release mode. It was awesome. Okay, the reference is much more verbose. Okay, so here's the reference. You should all look at this. To me, I got this sense of like some kind of low-grade beef between the Rustonomicon Unsafe Rust authors and the Rust reference authors, because the Rust reference authors, they write as if they have complete case coverage, and the Rustonomicon people say like, oh yeah, that standard's still being developed, there's no stable, whatever, blah, blah, I don't know. Anyways, here's a list of things considered undefined. And data races in here, dangling or misaligned pointers, but there's just like other stuff. Violating assumptions of the Rust runtime. Most assumptions of the Rust runtime are currently not documented. Great. Incorrect use of inline assembly. I decided to not teach inline assembly in Rust because I think it's unrustic. I don't know. But anyways, I do really like it that the Rust reference says when behavior is undefined is undefined. Okay. Previously in Rust, what is this? This dangling pointers. Wait, how many minutes do we have left?
20, 18.
Should I release you to do the lab? This is just a running example.
Do we still have a lab that we need to get in today?
You don't have to. Okay.
I feel like I thought that was part of the rubric was getting labs in.
Yeah, but because this isn't a full week.
Okay.
So I've also not done like a full homework this week. Safe Rust ensures references are always value. Borrows. What this means is every time there's a borrow, if you do something with the borrow, when you write the code and the code successfully compiles, you will not have your memory system explode. I just like saying the term frontier, so I put this here. The frontier between safe and unsafe Rust is the raw, which I prefer to call is the numeric pointers. And these are the star const or star mute. What does T represent? That's the generic type. So you can have a mutable or immutable pointer that Rust calls raw that I call numeric that points to any type of data. This is only for C people. So sorry, C people, I'm calling this out. This star in the type name is not an operator. It looks just like the C operator, but it's not. It's just part of the name. It's part of a proper noun. Raw pointers are inherently that should say aren't. I don't know what I mean here, but like you can create a raw pointer as long as you don't do anything with it. It's fine. That seems reasonable to me, right? Like, oh, I need some, like, it's not unsafe to have a car that can go faster than the speed limit, right? It's going faster than the speed limit that's unsafe. Okay. So what do we do? Raw pointers or numeric pointers. To me, it makes sense when you call them numeric pointers. You can ignore borrow rules because you can have mutable and immutable pointers to the same thing. You lose in exchange for this the guarantee that if you use them, your code won't explode. They are allowed to be null, so they are allowed to point to nothing. And I think they're allowed to leak memory. I don't actually know what automatic cleanup is, and I don't care, so I didn't check. So you can worry about that when you're writing performance-relevant Rust. Here's an example, and I can run this in safe Rust because I'm allowed to have a car that's too fast. I'm just not allowed to drive it that fast. Okay. What'd I do? Probably want to delete like a bunch of lines, right? That seems fine. I probably don't need these. Okay. So that runs. And what is this? I create a number. I made it mutable. And then I have both constant and raw pointers to it. Would this be allowed otherwise? No, I can't have two references to the same, or I can't have two. Yeah, they're called references, right? I can't have two references to the same object. I can with the numeric pointers because that just defines the number in program memory where that value is. Okay? Nothing unsafe. Creating a variable that refers to some value. After all, what's the worst thing that can happen? Nothing can happen, right? So this is all just language stuff. This is just setting things up. Nothing's actually executing here. Nothing's going on. The compiler can optimize out all of this stuff. It doesn't exist. It's imaginary. It's fake. It's just in source code. So we're allowed to do that. Separately, I personally myself am a brain genius, and I can perceive just by studying this code manually that there's no possible way there's any memory problems there because nothing's being done to memory. I'm not reading to or writing from memory. Okay, so that's definitely totally above board. Let's do something horrible. Let's just, pick a number. And here's a great number, 0, 1, 2, 3, 4, 5. One of my favorite numbers. Does anyone have a favorite number? What is it?
42.
42? Okay. I did a 42 joke in my AI class, and no one was into it. I felt like a boomer. Hexadecimal 42. Oh.
You can't translate the hex.
You can, well,
I mean, yeah, I can probably. Okay.
2, 8.
Yeah. Oh, that's so much harder in front of the classroom. By the way. Okay. All right. So here's. I bet this is unsafe, right? Doesn't this seem unsafe? No, you're smarter than Rust. You know this isn't. Well, okay.
You should put
Rust
an
is also this
underscore
one.
after the A and between the U size.
I should put an underscore here.
Yeah.
Why?
Why don't I also put an underscore
I don't
here?
like that.
Just to show that you can.
Can I also put one here?
I think so.
I think I can. Okay. Wait. Okay. Okay. When you said underscore, I thought you were suggesting this one, actually. And then I listened to the rest of your sentence. Okay. So that's allowed. That's safe. Let's do something terrible. We can dereference. How am I going to dereference? I'm going to do my favorite thing. I'm going to exceed the speed limit.
Still being recorded.
My favorite thing is to drive the legally posted limit or lower exactly. I don't know why I looked up how to print a variable in Rust. I definitely know how to do that. Okay. Can I just do this? What am I going to do? Star R. This will probably be fine. Okay. I did something weird in Vim there, but in my defense, that's because I forgot how to type letters. Okay? I don't know what the last key I hit was, right? And so it seems reasonable to me. Okay. I don't know what I did.
No, I don't know anyone knows what you did.
I don't know what I did either. Recover? Oh, no, I forgot to, I did X instead of. So that looks bad. Oh, that's not that bad.
Oh,
Must be.
It's not unwinding though.
So this should be a multiple of 64, 32. So let's just throw some zeros in here. Wait. Okay. How many zeros should we put in? Like 3? What? What's wrong with that? Which swap file do I want to use?
It's more recent. so-
Yeah, which one's more it's the top one, right?
Yeah.
No!
This is why you should learn how to configure bins so you can turn out the swap file.
Yeah.
That's why I should learn. That's the reason.
Yeah, wasn't that a
Hey! Oh, what's the segmentation fault? We say faulted rust! Is that what we were trying to do?
You gonna talk about mirroring at any point?
Sorry, what?
Mirroring?
No, I decided not to do that. I just got, nope, it's the end of class, dang it. I think Jimmy's allowed to talk about mirroring.
Yeah, when's that?
At some point.
We'll talk about, I think,
You can't really do it on non-hosted systems, so it gets a little hard for like operating system specific stuff.
I guess that's kind of true.
operating systems are cool. Okay, so, these are fake, I'm changing these. I think I have a better idea. I'm gonna try and get it to work this weekend. Okay, this is your lab. It's just a repeat after me lab. There's no critical thinking, you just work through the example. But you should have critical thoughts about it while you're working through the example. So go ahead and spend the amount of time you would like on there. Get something checked in for the sake of doing it, but this one's not like graded or grade relevant because of the partial week. So go ahead and take a look at that, have fun. I'm gonna go get some water and then I'll wander around the room and make snide comments. I might even say positive nice things.
I'll follow you and make snide comments about your
We're gonna be multi-snide commenting.